of onto, a function that maps onto its codomain, onto Rm. It is onto if t of x equals b has at least one solution. Yes, has at least one solution no matter what b is. And t is 1 to 1 if t of x equals b has at most one solution. And it's both 1 to 1 and onto. Exactly, right? Because it has to have at least one and at most one, which means it has to have exactly one. So I mentioned last class, I know you have a test in Calc 3, or many of you who are in Calc 3 have a test on Friday, and there's a test for us scheduled Friday in the syllabus, but I am going to push that test until Monday. Okay, so Friday, we're going to cover new material. So we're just going to swap Friday and Monday's classes. No, the material Friday will not be on the test. It's going to be chapter 1 will be the test. Friday, we're going to cover 2-1, I think. So that gives you a little bit more time to study and not have to take 2 tests in one day. And so for the test, you can use a graphing calculator to do row reduction. If you don't have one, I can lend you one. I've got plenty. You can bring 1 page of notes with you, front and back, that you make yourself. And I think that's it. You can have 2 hours. If you want, you can start at 10. Yeah, so 10 to noon. Okay, so today we're going to talk about the matrix of a linear transformation. We're going to look at the definitions of one-to-one and onto. And then we're going to learn how to find the standard matrix of a linear transformation and how to use the columns of the standard matrix to determine if the mapping is one-to-one and or onto. So I've got some notes here, as usual, just my sort of summary of the reading. You can check this out on your own. We'll touch on all these things in the demo. All right, so we're going to start with some old-fashioned functions that just go from real numbers to real numbers, things that you probably studied, several semesters ago. And we're going to determine if these functions map onto R and if they are one-to-one. So f of x equals 3x minus 4. Is it onto? Okay, so when I ask if a function is onto, or transformation, I'm asking, can I produce any output from the codomain? So the codomain of this guy is what? Real numbers. Okay, so the codomain is all reals. So my outputs are real numbers. Can I get every real number as an output using this function? Yeah. The range of this function is all reals, right? When the codomain equals the range, it's onto. Right? You can produce any element of the codomain as an image of the function. Yeah. All right. So how about one-to-one? Yeah, the first one, f of x equals 3x minus 4. We know it's onto, right, because we can produce any real number. We can produce the entire codomain as images of a certain input. One-to-one, when I ask if something is one-to-one, I'm asking, is each y in the range produced by at most one x from the domain? Yes. Pick any y in the range, 7, right? There's only one x that you can plug into this function and get 7 as the output. That's the at most one x, right? So this is one-to-one because any y is produced as the image of at most one x value. And you can see, you can check one-to-one and onto of a standard real-to-real function by looking at its graph, right? So 3x minus 4 looks like this. You can see that its range is all real numbers, and you go range equals the codomain onto. What was the test that we used for one-to-one for a function? Horizontal line test. Vertical line was to tell if it's a function. Yeah, the horizontal line test tells you if a function is one-to-one. This passes the horizontal line test, right? There's no two x values that produce the same y value. Okay, so this is one-to-one. Right, so f of x equals x squared is not one-to-one, because if you pick a y value, like 9, 9 is the image of two different x's, positive 3 and negative 3. Okay, so that one is not onto. I'm sorry, not one-to-one. Not one-to-one, because negative 3 and 3 both get mapped to 9. So 9 comes from two different x values, not one-to-one. All right, is it onto? No, because what's the range of x squared? Just positive numbers, 0 to infinity. That's not the codomain. The codomain is all real numbers. The range does not equal the codomain. You can't produce any y value you want using this function, right? Because you can't produce negatives. So my range is 0 to infinity, which does not equal all reals, the codomain. Sure, yeah, you can denote that as r plus union 0. So x squared, not one-to-one, not onto. How about x cubed minus x? Let's think about onto first. Why is it onto? How do you know that so quickly? What's negative? You can produce negatives, yeah. Right, so if you look at this is a cubic. The end behavior of a cubic is like one arm up, one arm down. So you're going to cover every single real number. You can get every real number as an output of this because of the end behavior. So this is onto. How about one-to-one? Why not? It's got a little dip. Flat spot, I don't know. You can produce 0 two different ways. What two x values give you 0 as an output? 0 and 1. Yep. F of so 0 and 1 both map to 0. So this is not one-to-one. You only need one counterexample. You just need one y value that comes from two different x values, and you're not one-to-one. So that's an example of a function that's onto but not one-to-one. So let's see, we have one that is both onto and one-to-one. We did one that was neither. Now we have one that's onto but not one-to-one. What do you think this one is? One-to-one but not onto, yeah. So let's see if we can explain why. So think about onto. What's the range of e to the x? 0 to infinity, just the positive reals, right? So I can only produce positive reals by plugging into the function e to the x. That does not equal all reals, which is my codomain. Right? So I can't produce every real number in the codomain. So that's r plus means positive reals. Yeah. So this is not onto. And how about one-to-one? Yeah. If you look at a graph of it, e to the x looks like that. It's going to pass the horizontal line test. There's no y value that comes from two different x values. That's enough of an explanation when you're dealing with a simple function from R to R. Yeah. So yeah, I just picked these basic ones to sort of help you digest the definition of one-to-one and onto before we start applying it to matrix transformations. So this one was not one-to-one, and this one was not onto. All right, so any questions about what one-to-one and onto mean? So onto, you can produce the entire codomain as images of the function. And one-to-one, no two x's go to the same output. No two inputs go to the same output. Okay, so now I'm going to do this for some linear transformations. So first, when I give you a linear transformation, every linear transformation can be written as a matrix transformation. So I just have to figure out what the matrix is that defines T, right? So A is called the standard matrix, right? And I have to figure out what goes in here so that when I multiply by 1, 0, I get 2, 6, 3. And when I multiply by 0, 1, I get 4, 0, 0. So here I've got some matrix A. And when I multiply by 1, 0, I'm supposed to get 2, 6, 3. And then that same matrix, when I multiply it by 0, 1, I'm supposed to get 4, 0, 0. So this the input vector x, what are its dimensions? 2 by 1. And the output vector, what are its dimensions? 3 by 1. So what does my matrix dimensions have to be? 3 by 2. Yes. Yeah, 3 by 2. So when you multiply two matrices or a matrix times a vector, the inner dimensions have to match, so the 2 and the 2, and then the outer dimensions give you the resulting vector, the 3 and the 1. All right, so this is a 3 by 2, 3 rows, 2 columns. So I have to figure out what goes there so that when I multiply by 1, 0, I get 2, 6, 3. Say it again. 2, 6, 3 would be the left column. Yeah. 2, 6, 3 and 4, 0, 0 the right one. Yeah. Does that make sense? So when you take the 2, 4 row and multiply by the 1, 0 vector, you get 1 times 2 plus 4 times 0, which gives you the 2. Right? So this whole right-hand column is going to get multiplied by 0, and I'm just going to get the 2, 6, 3 vector. And then if I do the same thing over here, 2, 6, 3, 4, 0, 0, my whole left-hand column is going to be multiplied by the 0 in this vector, and I'm just going to be left with the 4, 0, 0. Right? 2, 4 times 0, 1 is 2 times 0 plus 4 times 1, which is 4. 6, 0 times 0, 1 is 6 times 0 plus 0 times 1, which is 0. 3, 0 times 0, 1 is 3 times 0 plus 0 times 1, 0. So the lesson here is that if you know what T does to these unit vectors, we call them E sub i's, you know what the standard matrix is. Okay, it is completely determined by what T does to these unit vectors in the xi direction. So yeah, so if you look at my notes here, E sub I, E sub 1 is 1 with all zeros beneath it. E sub 2 is 0, 1, zeros all beneath it. E sub 3 is 0, 0, 1, and then fill in the rest of zeros. And E sub m, right, the last one, is all zeros with a 1 in the last spot. Just keep moving the 1 down a spot. Okay, so we've got the standard matrix that represents this linear transformation. It is 2, 6, 3, 4, 0, 0. You just take those as the columns. Now we have to know if this matrix transformation represents a one-to-one and onto transformation. Okay, so A, 2, 6, 3, 4, 0, 0. So my transformation T takes x's, actually I should say T of x equals AX, right? So it takes vectors and just as inputs and multiplies them by A. Is this transformation, is this function one-to-one or on and or onto? So let's think about onto first. Okay, so we said function's onto if it can produce any element in the codomain. What's the codomain of this thing? What kind of vectors do I get out? R3. So my codomain is R3, right? And I can tell from the givens, right? They gave me, they plugged in an R2 and I got out an R3. So I know that my codomain is R3. This transformation produces vectors in R3. And when I ask if it's onto, I'm asking, does it produce every vector in R3? Can I produce any vector I want to in R3 by taking a vector from R2 and multiplying by this matrix A? Right, so I'm asking, is my range equal to R3? So let's see. So I'm basically saying, if I pick any vector in R3, like B1, B2, B3, here's my A. I want to know if I multiply by x1, x2, is there an x1, x2? Is there a vector in R2 that will produce any arbitrary vector in R3? Does this have a solution? Okay, so if it has a solution, yes, I can produce any vector I want, right? And if it doesn't have a solution, then no, there is a B1, B2, B3 that can't be produced. Row reduce it? Yeah. So those aren't my notes. Where'd I put them? Okay. So I could say, well, I want to try to solve this system. 2, 6, 3, 4, 0, 0. Augment with B1, B2, B3, and row reduce it. Right? So I'm going to row reduce this thing. I already did it for you. And you can't have your calculator do it when you have variables in the last area. You don't, but I'm going to show you why. That's, yeah. For all B, for any choice of B1, B2, B3, is there always a solution? So when I row reduce this thing, I end up with 1, 0, 0, 0, 1, 0. And assuming I didn't make any mistakes, I have B2 over 6. Oops. B1 over 4 minus B2 over 12. And negative B2 over 2 plus B3. Is this thing always consistent? No, right? Because this says 0x1 plus 0x2 equals a number, right? That's only true if this number is 0. So there are definitely B values that can make this system inconsistent. Okay, so there are B vectors that make the system inconsistent. Okay, so Ryan, what were you going to say about not needing to do the B thing? Cool. It's actually each row. We're looking for a pivot in each row, right? Because it's this fact that 0x1 plus 0x2 equals a number. It's the pivot missing from this row that lets you know that that system's not always consistent. All right, so we don't even need to do this thing with the B1, B2, B3, right? All we have to do is take A, 2, 6, 3, 4, 0, 0, and row reduce it to 1, 0, 0, 0, 1, 0, and see that there is a pivot missing from row 3. Yeah, you're right. You're right. Yeah. You can tell just by looking at it that there can't be a pivot in every row. So there's not a pivot in every row. That means that this thing is not onto. Right? There are B1, B2, B3. There are vectors in R3 that we cannot produce by multiplication by A. Right. Right. Yeah. Okay, so let's look at the same matrix, 2, 6, 3, 4, 0, 0. Same matrix transformation. We're going to see if it's 1-to-1. So T of x equals AX, where A is 2, 6, 3, 4, 0, 0. Okay, so 1-to-1 1-to-1 we can say that there's at most one solution. Either there's none or one. Okay, so is there at most one solution that's one or none, right, to AX equals B? No. The row reduced echelon form has a place, right? So let's just copy the B1, B2, B3 row reduced echelon form. This thing here. Why do you think that, Todd? Ah. Yeah. So say that one more time. Yeah. Yeah. So inputs are x1, x2. Inputs are from R2. So you need to come up with two different vectors from R2 that could give you the same output. So you're only talking about B's right now? Like you're saying there's different ways you can create a 0 as the output from B? Are there any let's just assume that this might not have a solution, right? So we've satisfied the none, right? Sometimes it has none. So when there is a solution, is it the only one? When this has a solution, is it unique? Only when what's 0? Yeah, right. So like just assume that this number actually is 0, right? So this has a solution. When this has a solution, right? And that only happens if negative b2 over 2 plus b3 equals 0. So assuming this has a solution, is it unique? You're right. Yes. Yes. I have this wrong on here. So what is telling you that it's unique? How do you know? Yeah. It says x1 equals this number, x2 equals this number, right? So it's unique. So it's the fact that there are no free variables, right? There are no free variables. So when a solution exists, it is unique. Right? So there is only one vector, x1, x2 in R2 that can produce a given b1, b2, b3 from the range. Okay, so what other thing have we studied that you can answer by saying whether or not it has free variables? Independence, yeah. So we know that T of X is 1-to-1 if the columns of A are linearly independent. That's the same thing as asking whether or not there are free variables. It's the same thing as checking if there is a pivot in every column, right? Right, so this is 1-to-1. So this thing was not onto, but it is 1-to-1. All right, can I write a little summary for you? T of X equals AX is onto if A has a pivot in every row. Because that tells you that AX equals B has a solution for every B. Okay. It is 1-to-1 if A, so the columns of A are linearly independent. And you check that by looking for free variables or solving the homogeneous system AX equals 0 if that has just one solution 1-to-1. Right, that's what it means to have linear independence. So we've done a lot of work, like really forcing our brains to think about what it means to be 1-to-1 and onto. But we were doing a lot of unnecessary work. Now that we have sort of equated in a matrix transformation, it's onto if A has a pivot in every row, it's 1-to-1. If the columns of A are linearly independent. Now it should be very quick to answer questions about 1-to-1 and onto. So I'll do one more example with you, and then you can try some. Okay, so T goes from R5 to R3. So T of X1, X2, X3, X4, X5 produces vectors in R3 that look like X3 minus X4, 6, X5, 0. So I'm trying to figure out what matrix A has to look like so that when I multiply by X1, X2, X3, X4, X5, I get X3 minus X4, 6X5, and 0. How many rows do I have in this thing? 3. So this is going to have to be a 3 by 5 matrix, right? Because when I multiply by a 5 by 1 vector, I get a 3 by 1. Okay, so my first row, it's going to have 5 entries in it, so that when I pick it up and turn it 90 degrees and line it up with the vector, everything has a match. Every entry has a match. So how many x1s do I need? None. To get x3 minus x4, I need no x1s and no x2s. I need a 1x3, negative 1 x4s, and no x5s. Does that make sense? So I'm imagining picking up this vector, and it's got 5 placeholders in it, right? I line it up and put it on top of here. You multiply the things that line up, and I'm saying I have no x1s in the result, so I've got to have a 0 here. There are no x2s in the result, so there's another 0. There's a single x3, so I have a 1. A negative x4, so I have a negative 1. And then there are no x5s in the result, so I put a 0 there. All right, so what does my next row have to be? Yeah, 0, 0, 0, 0, 6. So that when I multiply this row times my vector, I get 6x5. And then the third row would have to be all zeros to get 0. Okay, so this is my standard matrix. It's called A. Standard matrix A. Now I want to know if the function t, the transformation t, is 1-to-1 and onto. Okay, so let's see. 1-to-1. We're asking, are the columns of A linearly independent? So let's take a look at the columns of A. Linearly independent? Why not? There is not a pivot in each column, correct? That's one way to recognize it. How else could you recognize that they're not linearly independent? There are free variables, same thing, yeah. So we'll say no, and then we'll put a bunch of reasons why, right? So there's not a pivot in every column. There are free variables. And those are both really good ways of recognizing this. When I looked at this, I said, look at this vector and this vector. Is one a multiple of the other? Yeah, that makes it not linearly independent, right? If any vector can be written as a linear combination of the others, then it's not linearly independent. So 1, 0, 0 is -1 times -1, 0, 0, not linearly independent. So it's not 1-to-1. Let's think about whether or not it's onto. So the question of onto can be asked by saying, do the columns of A span R3? Do the columns of A span R3? Can I produce any vector in R3 by multiplication by this matrix? No. Like, what kinds of vectors get left out? Anything that has a number in the third entry. Yeah. So for example, so I don't even really have to think about A in this question. I just have to think about what onto means. So my codomain is R3, but I can't produce every vector in R3 because I only produce vectors in R3 that have zeros in the third entry. So this is no, because, for example, vector 1, 1, 1 is not in the range, right? You can't produce anything that has a non-zero third entry. So the range does not equal the codomain. You can't produce every vector in R3. If I wanted to answer this via the matrix A, I would just row reduce A, and there's not a pivot in every row. So A ends up being equivalent to, oh, I didn't do it because I said it's too easy to answer the other way. Well, you already have a row of all zeros, right? So you know you can't have a pivot in the last row. So you would say not onto, because A doesn't have a pivot in every row.